Stimulated emission of photons. In this video we'll cover the stimulated emission of photons and also lasers. So it has been discovered that when a photon is incident on a material and that photon has the energy that corresponds, and that photon corresponds to a transition from a higher energy level to a lower one, the photon can actually stimulate the emission in that it forces it to that ground state. The photon that was incident still exists, but a new photon is created because of that transition to the ground state. So what this results in is two photons, both have the same energy, same direction, and same phase. So I'll go through a couple of definitions that will build up into how lasers work. So in a gas, when more atoms are in an excited state than the normal state, this is called population inversion. So this can be achieved by bombarding the atoms with photons of the exact energy level that's required, which promotes those electrons to the energy level that we're looking at. A high voltage can also be applied to achieve the same result. Another definition is metastable state. So this is when the electrons in the higher energy levels stay there for a little bit longer than normal. Some atoms have energy levels that are metastable states, where most of the time the electrons that are at those levels would like to return to the ground state straight away. Now, for practical reasons, to achieve population inversion, a metastable state is required. Laser is actually an acronym, and it stands for light amplification by stimulated emission of radiation. We will look at a particular case of a helium neon laser, and the components of it consists of the gaseous medium, a pump that supplies energy to the tube, so that excites the electrons to the energy level that we're interested in, and other components that amplify the light, including a fully reflective mirror and a partially reflective mirror. So the reason why helium and neon are chosen as the gas that we use in lasers is because helium and neon have energy levels that correspond very close to each other. In a laser, the helium is heated up and the electrons are promoted to energy level 1, and when they drop back down, photons are released, which stimulate the neon. Now, the electrons in neon that reach level 3 reach a metastable state, which means they are there slightly longer than normal, meaning there's a lot of atoms in this state. Remember, population inversion. So what this means is that when these electrons return to the ground state, there's a lot of photons that are emitted with this exact energy. Now, these emitted photons are captured long enough in the device to further stimulate more photons of the same energy. Now, finally, the light that is produced is obviously the same energy due to the energy level drop, in phase and coherent. So the benefits and applications of lasers include that the beams can be of very high intensity, meaning they don't spread out over large distances. They are monochromatic, meaning they have the same frequency or wavelength. Unidirectional, where they don't diverge much when they leave the tube. And also coherent, so they stay in phase over long distances. Now, when using lasers, there's a lot of safety to be considered, such as the operating instructions of the laser that you have. Don't shine the laser into a person's eyes, as the heat damage and the intensity of the light can cause permanent damage. Avoid reflecting surfaces, and use lasers in a well-lit room to reduce the aperture of your pupil, which reduces the risk of the laser actually entering your eye. Lasers are used in many fields, such as the laser airborne depth sounder, which measures the depth of water, and that was actually invented in Adelaide. Reading data of CDs, if of higher energies, welding metals and cutting through metals. Measuring distance with high accuracy, many medical applications, and computers and communication. Compare the process of stimulated emission with that of ordinary emission.